Good morning, students. Myself, Vijay Shankar from ECE Department, Chevrolet Engineering College. Today, I are going to discuss about the applications of a Smith chart, how to construct the Smith chart, and how to find the parameters for the given values. So the applications of the Smith chart. Let us consider a few applications of Smith chart through an example. Consider a 30-meter long lossless transmission line. Here they are saying that a 30 meters long lossless transmission line. Lossless means, first of all, you can know that the lossless is alpha is equal to 0. Lossless transmission line. A 30 meters long, the given 30 meters long transmission line with the characteristic impedance of 50 ohms. Characteristic impedance means it's a Z0. 50 ohms. Operating at the 2 megahertz. 2 megahertz, the frequency is hertz means it's a frequency. F is equal to 2 mega 10 power of 6 hertz. If the line is terminated in impedance 60 plus J into 40 is terminated means ZR at load end. ZR is equal to given is a 60 plus J into 40. Got it, my students? And calculate the reflection coefficient. Means they are asking that is a reflection coefficient. What is the reflection coefficient? The standing wave ratio means S is equal to the input impedance Z in. If the velocity of velocity on the line is V is equal to 0.6c, have to find out all these three. When the given the velocity is also given, that velocity is V is equal to 0.6c. That C we know the standard value, the 3 into 10 to the power of 8 meters per second. So one example. By using this example, you have to know a few examples. You have to find few applications of the Smith chart to this example. So first of all, you have to find out the reflection coefficient. The reflection coefficient. They're asking that by using this given data, we can find out the reflection coefficient, standing wave ratio, input impedance. If the velocity of line is V is equal to 0.6 c, the reflection coefficient K is equal to, or we can also represent the reflection coefficient is a gamma also. K is equal to, we know, ZR minus Z0 by ZR plus Z0. You know this formula, my dear students. What is the ZR given? 60 plus. So K is equal to 60 plus J into 40 minus Z0. What is the Z0 here? Minus 50 whole divided by ZR plus Z0. 60 plus J into 40 plus 50. So that is equal to, in the numerator, 60 minus 50 is a 10. 10 plus J into 40 whole divided by 60 plus 50 is a 110 plus J into 40. Okay. So here the 10 plus 40J and 110 plus 40J. By using your calculator, convert this rectangular form to the polar form. So what is the rectangular form? Under root of R square, X square plus Y square. What is the X here? 10 means 100. 40 square. Again, you'll get the 40 square, the 40 into 40. 1600. And under root value, the 41.23 with an angle of 75.96 degrees. By using a calculator, you can convert the rectangular form to the polar. In the denominator also, you can same thing. And these two are divided with the value, you'll get the 0.352, and angle is 75.96 minus 19. Okay, let us, this is 76 minus 20. 76, approximately value is a 76, and this is a 20 value you can consider. 70 minus 20, what is a 76 minus 20? 56. These two can divide, you get the 0.3. The K is equal to, the magnitude is a 0.3523, and angle with 56 degrees. Okay, my dear students, we got the reflection coefficient. Okay, by using the formula ZR minus Z0 by ZR plus Z0, you can find the reflection coefficient 0.3523, angle of 60 degrees. 56 degrees, sorry. And the second one, the standing wave ratio. Standing wave ratio, the relation between of reflection coefficient and the standing wave ratio is 1 plus the reflection coefficient by 1 minus reflection coefficient. This is a magnitude, not the angle, my dear students. S is equal to 1 plus the reflection coefficient magnitude by 1 minus reflection coefficient magnitude. What is the magnitude here? 0.3523. So you can add to the 1 and subtract from the 1. You get 1.3523 and 0.64. You can calculate this one. You get the 2.08. Is a S. S is equal to 2.088. These are all the theoretical values, my students. By using the Smith chart also, you can find out the same values, whether you are getting the, by using the Smith chart or not. These are all we are finding the theoretical values of. And the velocity of the line is given V is equal to omega by the beta, propagation velocity. Beta is equal to omega by V. And what is omega? Nothing but 2 pi f. And V is given, that V is also in terms of V is equal to lambda f. Okay, the V is equal to omega by beta, that is beta is equal to omega by V. But the electrical line of length of the line is Bs, where S is a 30 meters. 30 meters is given. Beta is equal to. So beta S is equal to omega by V to S. Omega is a 2 pi into F and V into S. To find the length, given the length is a 30 meters long lossless transmission line with a characteristic impedance. So the S is nothing but here the L, BL, beta L. So cos hyperbolic beta L, where L is a cos hyperbolic beta x and sin hyperbolic beta x. In the equations we already know. ZR into cos hyperbolic gamma x and sin hyperbolic gamma x. R is a gamma is nothing but the P there. That P is the propagation constant of the gamma is also the propagation constants. And X is the length of the transmission line. That length of the transmission line is a L. So the beta L are here they are representing as S, beta into S. So beta into S, 2 pi f by V into S, 2 pi f. Given the frequency, what is the frequency given? 2 megahertz, 2 into 10 to the power of 6, and 30 meters here given, 30, and 0.6 into 3 into 10 to the power of 8 is a velocity. Given the velocity of propagation is a 0.6 into 3 into 10 to the power of 8. Calculate this one totally. We'll get the 120 degrees in terms of degrees, or in terms of the radians, 0.6666 into the pi. Okay, we got the beta into S also. So beta into S is 120 degrees. Standing wave ratio is 2.088. And the reflection coefficient is magnitude is a 0.3523 and angle is a 56 degrees. So reflection coefficient we got, standing wave ratio we got, and we need the input impedance also. For this input impedance only, we are finding that is a beta S with the velocity. The input impedance if the velocity on the line is V is equal to 0.66. Okay. What is the formula for the Z in? Z in is equal to R naught. R naught is nothing but the Z naught only minus. We already know this is a formula. The Z in is equal to input impedance Z naught into ZR plus J into Z naught tan beta L whole divided by Z naught minus J into ZR tan beta L. This is a formula we already know, and we already derived this input impedance function. Z in is equal to, what is the Z naught given? 50 ohms, and ZR is given with 60 plus J into 40 plus J into 50 tan beta L. Now what is the beta L? Nothing but get the beta S on. This is 120 degrees. 120 degrees whole divided by Z naught is a 50 minus J into 60 plus 40J ZR 40J and tan beta L tan 120 degrees. Okay, my dear students. And calculate the function here, the 50 whole multiply with the 60 plus, both are is a J into 40 plus 50 into tan 120. Find the tan 120 degrees from your calculator and multiply with the 50 and add the 40. The numerator becomes a rectangular form, 60 plus J into whatever the value we got. And here the 50 minus J 60 and minus J square will becomes is a J plus 1 40 and whole multiply with the plus 50 plus, let us take tan 120 degrees. Okay, my dear students. So the 50 into, convert this into the angle, 60 plus J into the value will get the rectangular form, convert the magnitude and the angle. And similarly here also 50 plus 40 tan 120 is a real term minus J60 into tan 120, that is the imaginary term. Here also you can find out the magnitude and the angle, then multiply with the 50. Okay, finally they got the value is Z in is equal to 24.01 with an angle of 3.22 degrees, or otherwise in the rectangular form 23.97 J 1.35. So all the values we got, the reflection coefficient and standing wave ratio and the Z in is equal to input impedance by using the velocity. Okay, and these are all the theoretical values. By using the Smith chart, you can find out the reflection coefficient, standing wave ratio, and the Z in also. Okay. Now, applications of plotting of an impedance. Plotting of an impedance. So we theoretically find out the values. We got the reflection coefficient and standing wave ratio and also the input impedance. Now you can plot the values in the Smith chart. How we can plot? The first point is plotting an impedance. Any complex impedance can be represented by a single point on the Smith chart This point is nothing but the intersection of constant R circle and X circles. That R circle is RR by R naught and X circle is J into XR by R naught circles. Otherwise, in terms of the normalized, they are saying, consider the above example, ZR is equal to RR plus J into XR. What is the RR here? The 60 plus J into 40. The 60 is RR and 40 is the XR. Okay. So totally is RR plus J into XR divided by the R naught only, the normalized impedance. ZR by the Z naught. ZR by Z naught. What is the ZR given? 60 plus J into 40 by the 50. So 60 by 50 is a 1.2 and 40 by 50 is a 0.8. And this normalized impedance you can plot on the Smith chart and locate a point P with R circle is 1.2 and J circle X circle is a 0.8. So locate a point P on the Smith chart where R is 1.1, R circle is 1.2 and X circle is a 0.8 and meet together. The intersection of the two circles is represented by a dotted lines and the point P indicates a normalized impedance on the chart. Okay, now you can see that how we can plot that normalized impedance 1.2 and J 0.8. See, this is a graph we have. In this graph, see, there is a point P there. Is a point P means, and here you can observe there is a 1.2 circle is there. This circle is a 1.2 circle. Observe, my dear students. Here, to get the point P, it is intersected the R circle and this R circle and X circle. That point is a P. What is the R circle here? 1.2 and X circle is 0.8. 1.2 and 0.8. Let us see here the 1.0 is the center here. And next line is I am showing here. The first one is here is a 1.0. And this line of next circle is a 1.1. Next circle is a 1.2. And this is a 1.3, 1.4, 1.5, and up to the so on. It is the infinite. It is the infinite. Okay. So I need to plot R circle is a 1.2. This is R circle, my students. Okay. This R circle is the total circle is a 1.2 circle only. So this is a circle, and I need the X circle also. That X circle starts from here the 0. This line is a 0, and so on. It is increases. Go on like this. It is increases. Okay. Let us see that also. See, this is a 1 point. I think I need the 0.8. This line, this circle is a 0.8. See here. This is a 0.8, my students. This line is a 0.8. So on. See here, the crash is the 1.2 circle. 1.2 circle. You see all the values here is a 0.8 and 1.2. Got it, my dear students? Now mention that in the intersection point is a P. Okay, the intersection point is a P. We got normalized impedance is 1.2 and J 0.8. So locate a point P on the Smith chart where R circle is a 1.2 and X circle is a 0.8, and they meet together. The intersection of the two circles is represented by a dotted lines, and the point P indicates the normalized impedance on the chart. Okay, my dear students. Now, the measuring of the VSWR, voltage standing wave ratio. After plotting the normalized impedance, you can determine the value of VSWR by drawing a constant S circle with the center of the chart, and the radius is equal to the distance between the center O and the point indicating the normalized impedance. Means in the circle, suppose this is a Smith chart like this. The center point is at 1.0. Now we plot a point P, normalized impedance, with 1.2 circle, R circle, and X circle is a 0.8. With this distance, let us take it is a distance from O to the point P. Draw a S circle with the radius of origin to the point P, with the distance center with O. Draw a circle, and this circle is meet at baseline. The baseline here, that value is S. Nothing but standing wave ratio. After plotting the normalized impedance, nothing but this one, normalized impedance, we can determine the value of VSWR by drawing the constant circle, S circle, with the center of the chart, and the radius is equal to the distance between the center and the point indicating the normalized impedance. Then the point of intersection of S circle with the real axis at the right side of the center indicates this is a center and this is a real axis. Then the point of intersection of S circle with the real axis at the right side, consider this is a real axis here, and towards the right side of the center indicates VSWR for the given line. VSWR for the given line. Consider the above example. Select a center with a circle O as a point O. Take a distance from O to P, indicating the normalized impedance, and then draw a circle. The circle cuts the horizontal real axis, the point Q. This indicates the value of VSWR for the line considering as shown in the figure. So what is the value we got? The standing wave ratio previously in the theoretically we got standing wave ratio is a 2.088. After drawing this S circle with the radius of the distance from origin to the point P, it crosses the exactly the 2.088 circle, or approximately the 2.088. Okay, let us see that circle whether it is crosses the same value or not in the Smith chart. See in the Smith chart, this is a S circle. So whatever they are showing is a dark S circle. So here it is a S circle. With the radius of 0 to P value. That P is a 1.2 circle. (1.2) plus J into 0.8. From the origin, let's see what is the value of this one. What is the value? So here the 1.2 already the circle is there, and next is a 1.5, and here the 1.8. Then is a 2. It crosses the 2 here. So 2 point something. This is a value of the circle is a 2 circle. This circle, R circle is a 2 circle. So it is approximately we got the 2.0, and theoretically we got the 2.088. Got it, my dear students? We got a VSWR, voltage standing wave ratio. Voltage standing wave ratio. And also to find the reflection coefficient, gamma is equal to its magnitude and angle theta r. So now what is a theta r? We got previously, that is a value of 1.0, 1.2 and 0.8. In the reflection coefficient, the reflection coefficient magnitude is equal to the distance of OP and OQ ratio. What is a OQ ratio? OQ distance means after plotting the point P from origin to the P, extend this line up to the Q. Extend this line up to the Q value here. This is a Q. And now, by using the scale, you can find out the distance from origin to the point P and also the origin to the point Q, and find the ratio between those two. We'll get the reflection coefficient magnitude value. And then by using the protractor, you can find the angle of these two. Point to the origin to the point P and the point S value here. Find the angle here, angle theta r. We got as a theoretically it is a 56 degrees. Is approximately how to get this angle is also the 50 degrees. Okay, my dear students. I think the magnitude of reflection coefficient and angle R is 0.3 with an angle of 56 degrees. And the theoretical value. That 0.3 you get from this line, the distance from O to P and the distance from O to Q, the ratio will get the 0.3 approximately. Okay, so by using this Smith chart, we got a reflection coefficient, magnitude and angle, and standing wave ratio also. That is a 2.0. And another one you have to find out, that is a Zin. Zin is equal to input impedance. How we can find that input impedance? You can extend this line. I'm saying that is a 0 O to the point P and O to the Q. Extend this line towards the backward, and wherever it is crosses the S circle. Once again, I'm saying, my dear students, the 0 to P, the distance we are taking, and O to P, 0 to the Q. So that line is extended backward to cross the line circle of S circle. Wherever it is crosses, find those values in terms of R, and the bottom line we can say R minus J into X. Above the bottom line, that is R plus J into X. That is, we pointed that is a 1.2 R circle and the J into 0.8, the normalized impedance. Normalized impedance. And after the extended this line towards the backward and place a point that is a P dash. That P dash is R minus J into X. R minus J into X, because the below the bottom line, all the values, the imaginary values is a negative sign on. Got it, my dear students? You'll get that is an admittance also. From the impedance, we can find out the admittance, and by using the admittance, we can find out the impedance. See the next one. We understood how we get the value of S from the circuit. Now, the second one, next one, measurement of the reflection coefficient K. The angle of reflection coefficient K is obtained by extending a line from the center to the outer rim of the chart. Outer rim of the chart through the point which indicates a normalized impedance. The point at which the extended line cuts the outer rim gives directly the value of angle of reflection of the coefficient K. In the commercial Smith chart, the K6 scale is provided at the bottom of the chart. Then, by selecting the point center on the scale, draw an arc just intersecting the straight line of the voltage reflection coefficient with radius is equal to the distance between the center of the chart and a point indicating the normalized impedance. Then the distance from the center to the point of intersection of the horizontal K cycle gives directly the magnitude of the K. We'll get the reflection coefficient and the magnitude. Okay, from the transmission line considered from the above example, draw a straight line starting from center and extending up to the outer rim through the point P. This line intersects the outer rim at the point M. M is a Q, okay, which indicates the angle of K as shown in the figure that at M the angle is a 55.5. Similarly, on the K scale, at the bottom of the chart, the arc drawn with the radius equal to the OP intersects the horizontal line at N, and its magnitude is a 0.35. Means the ratio between of OP, the distance, and the OQ distance is a 0.35, and angle is a 55.5 degrees. Okay, my dear students. Then, to find the input impedance, we already find out that is a S is equal to lambda is equal to 90 meters, V is V by F, and S is equal to 30 meters. It is a 240 degrees. For the above transmission line example, the total length is given to 30 meters. Let us first calculate in terms of the lambda, because the lambda is a transmission line length. Lambda is equal to V by F, or F is equal to V is equal to F lambda. This 0.6 C by F, and 0.6 into 3 into 10 to the power of 8, and F is given the 2 into 10 to the power of 6, 90 meters. S is equal to 30 meters, length is given. So 30 meters, 30 by the 90 into lambda. In terms of the lambda, you have to find out. So for the given S is equal to 30 meters, you can convert it to in terms of the lambda, nothing but the degrees. 30 by 90 into lambda is lambda by 3. What is the lambda? Nothing but is 720 degrees. By 3 is a 240 degrees. So whatever the angle is there, the 0 to P, extend that is a 55.5 degrees towards the anti-clockwise direction up to the 240 degrees. Up to the 240 degrees. Now in the chart, the line OP is extended up to the outermost scale, cuts at the point E says, the distance corresponding to the point E is a 0.173 lambda. Okay, so you can use this all the values, whatever we got from the Smith chart. That E is a 0.173 lambda. Then move from the point E, and the distance is equal to the 0.33 lambda in clockwise direction to reach generator point F as shown in the figure there. Now, total distance to be traveled the 0.33 lambda from the point A. The extreme right point crossing the corresponding to the 0.25 lambda is given as 0.25 lambda minus 0.173 lambda, that is a 0.077 lambda. Okay, and by using these values only, we got the Zn is equal to 0.48 plus J into 0.35, and these multiply with the Z naught. Whatever the impedance we got from the chart, Smith chart, that is a 0.48 and J into 0.35. Okay, the point of intersection on the line from O to T, and the constant S circle is represented by the point T, which is the intersection at the R is a 0.48 circle and X is a 0.35 circle. And this Zin is multiplied with the Z naught to get the actual input impedance what we find in the theoretical value. That is, Zin is equal to 50 into 0.48 plus J into 0.035 is 24 plus J into 1.75. Is approximately equal to the Z in the theoretical value. Okay, so note of the point lambda is here. Up to that is you can extend the 244 degrees to get the point P dash, or otherwise whatever the R circle and X circle is crosses here, that is nothing but the Zin. That Zin is multiplied with the Z naught to get the actual input impedance. Actual input impedance. Got it, my students? So by giving the values, whatever you are getting the load impedance and the characteristic impedance of Z naught and ZR, and the frequency is given, and also the velocity, at the velocity V is equal to 0.6 C, find the Zin value. By using the Smith chart, you can find the magnitude of the reflection coefficient and angle of the reflection coefficient. Magnitude of reflection coefficient is the distance between the, take the distance of 0 to P and 0 to Q or 0 to M here. The ratio of that 0 to P and the O to M is a reflection coefficient magnitude, and whatever the angle is here, that angle is a theta, and with this radius you can draw a circle showing that is a S is processed here. Standing wave ratio, it is approximately 2.088, and then extend this value, this line up to the crosses the S line, S circle, sorry, and name it as a P dash, and find the R circle and the S circle, X circle crosses from here, and whatever the impedance we got, R minus J into X, multiply with Z naught, we get Zin value. Okay, by using the Smith chart, we have to find out the reflection coefficient, both magnitude and the angle, and with the radius of O to P, we get the S value, and extended this line and find the impedance and multiply the 50, we get the input impedance. Got it, my students?